Hello and welcome back to Calculus 2, section 10.3, Calculus in Polar Coordinates. And this is the last section of the semester. Oh, I know. But don't worry about it. We continue this in Calc 3 with 11.1. Yeah. So, what is happening now? We know polar coordinates from last class. We know that the polar coordinates complement rectangular coordinates, which you guys are used to. We know that, in quotes, what's ugly in rectangular coordinates is beautiful in a polar world, and what's beautiful in a and vice versa. There you go. I forgot which one I said, so you know what I want to say. And we also seen parametric equations, so these three sections will be heavily used in Calculus 3. We start with the notion that the point in polar coordinates is written as r theta, where theta is independent variable. And we also have the function, which is r as f of theta. And here is that independent variable again. So theta is the input and r is the output. Now I know that you're used to x comma y, and x, right, was input and y was the output, and they were written backwards, right? But, you know, just deal with it. What's important to realize here is that theta is the input. So you're no longer placing your input values from 1 to 7. You are going to do it now from pi over 4 to pi over 2, and you are swiping off an angle. So technically, when you think of a large pizza slice, right, a large pizza, and you slice it into 8 slices, like this, this one slice here is from 0 to pi over 4. And then it's pi over 4 in terms of the, if you want to say, some angular width or whatever. And then you have the next one from pi over 4 to pi over 2. It's also pi over 4 in width, right? Over here, it's pi over 4, and over here, it's pi over 4. So each one of these slices is pi over 4 in width, but the location of the slice is actually determined by the input and the output angle. So this slice over here is going to start at 1, 2, 3, 4, 5 pi over 4, and it's going to end up at 6 pi over 4, which is actually 3 pi over 2, which we know it cancels to it, right? So even though this slice is the same width, or it looks the same as any other slice, it's pi over 4 in its angle, right? The location of that slice is different. Now this is going to be crucial for your Calc 3 when you have a function that is built on top of this. But right now, as far as we're concerned, it's in 1/8 of a circle, and the location is going to be determined by these guys. And obviously later when we set up the integral, it will be these guys in limits to figure out the area between certain values. So we start first with the derivative. We know that we can get a whole bunch of different shapes for our from our polar coordinates. We talked about a few of them. So I believe we did r equals 4 sine theta, right? No, 4 sine 2 theta. And that gave us a flower. Like this. That was number 4 right there. And that was number 4 over here. So that gave us a flower. But this is still graphed on xy. Yeah, I understand this is not a function, and if I try to do vertical line test, it's going to fail miserably and all of that stuff. But I can still pick a point somewhere and strike a tangent line through it. Now that tangent line has a slope, and that slope is dy dx. So there is a way for us to compute dy dx derivative. But look what we're given. We're given r equals 4 sine 2 theta. So what does that mean? That means that we have to figure out the formula to find the derivative of x and y in terms of r and theta. And we should be okay with that because we know the formulas that connect the two worlds. So I'm going to derive it quickly. As a student, I did not memorize this formula. I actually derived it every single time because it's really straightforward. It involves product rule. So it shouldn't be that difficult. So what do I know? I know that the slope is going to be this dy dx. So I am in a search of dy dx. Now if we use the clever thing, right, we are going to get dy d theta divided by dx d theta. Because I can do that, right? Now, this is d theta of y, and this is d theta of x. And don't I have those conversion formulas that we memorized? Y equals r, x equals r cosine theta, and y equals r sine theta. Do we have those? Sure, we have those. So now your derivative dy dx becomes the derivative in respect to theta of r cosine theta divided by, no, that's a y, so it's a sine. And then d theta of x, which is r cosine theta. There we go. Now to take this derivative, we have a product rule there. Because remember that r is a function of theta. If r is a function of theta, that means that r times any kind of other thing is going to be the product rule. So, r is, copy the first, derivative of sine is cosine theta, plus copy the second, which is sine theta, times the derivative of r in terms of theta. So that better be r prime of theta. So copy the first, derivative of the second, plus copy the second, derivative of the first. It's a product rule. Denominator, same thing. Copy the first times derivative of the second, plus copy the second times derivative of the first. Great. So now, what I want to do is make this cleaner. I don't want to start with a negative sign, and I want to keep r's with r's and primes with primes. So swap the order of terms, right? And just clean it up. So what's dy dx when polar coordinates are given? It is going to be r prime of theta times sine theta plus r times cosine theta, r of theta, right, times cosine theta, divided by r prime of theta cosine theta minus r of theta sine theta. So you have a choice to do quick product rules or memorize the derivative formula. This might pop up on the final, I don't know. So now, if you are given that your r, which is the f of theta, is equal to 4 sine 2 theta, and your theta, right, is equal to, I don't know, you want to find the tangent line at, say, give me a value in terms of radians. What happened? Did you just say pi over 6? Okay, fine. So pi over 6. That's what I heard. Next time, act faster. It's just voices in my head all the time. To find the slope, all you need to do is to plug this in, and you're done. So what do we have? We have dy dx is equal to long line, and then we go r prime of theta. Well, that's the derivative of sine, that's a cosine, and let's do that's 8 cosine 2 theta times sine theta plus 4 sine 2 theta times cosine theta. If I need to color code this out, fine. Here's your r prime. Here's your sine. Here's your vanilla r. And here's your cosine. And just follow that. On the bottom, we have the same deal. 8 cosine 2 theta times cosine theta minus 4 sine 2 theta sine theta. So, to get m, plug in theta equals pi over 6. So what do I do? M equals dy dx computed at theta equals pi over 6. Well, again, long line. I have 8 cosine of pi over 3, right, because it's double, pi over 3, times sine of pi over 6, plus 4 sine of pi over 3, times cosine of pi over 6, divided by 8 cosine of pi over 3, times cosine of pi over 6, minus 4 sine of pi over 3 times sine of pi over 6. So slope is 8 cosine 3. So cosine of pi over 3 is a cosine of 60 degrees, which is very good. Times sine of it, very good. Plus 4 sine of pi over 3, nice. Times the cosine of pi over 6, yes. Divided by 8 times cosine of pi over 3, very good. Cosine of pi over 6, very good. Minus 4 times sine of pi over 3, very good. And sine of pi over 6, very good. All right. Now, instead of computing this like a lunatic, I'm going to multiply numerator and denominator by 4 and kill all the fractions. So, times 4 and times 4, and that kills all of the halves. And you are left with 8 plus root 3 times root 3 is 3 times 4 is 12. And on the bottom, you have 8 root 3 minus 4 root 3. Well, that's much easier. 8 plus 12 in my book, 20, divided by 4 root 3. Divide by 4 and multiply by root 3. So 20 divided by 4 times root 3 is 5 root 3, divided by 3. There's your slope. 5 root 3 over 3. Tangent line is y equal mx plus b. So now I have to find x and a y, right? Well, x is r cosine theta. So that means that x is 4 sine 2 theta cosine theta. Right? Because r is given as, so all of this stuff over here is r, because that's given in a formula. And theta is equal to pi over 6. Yes, we all agreed, right? So you found your x. It's 4 sine of pi over 3, which is root 3 over 2, times the cosine of pi over 6, which is also root 3 over 2. So this is just 3. Beautiful. And the y value is r sine theta, which is y equals 4 sine 2 theta sine theta. So y is equal to 4 times sine of pi over 3 is root 3 over 2. And the sine of is 1/2. So this is just root 3. Yay. Y is root 3. Slope m is 5 root 3 over 3. X is just 3 plus b. These die. And b is equal to negative 4 root 3. So what's the tangent line? Y equals 5 root 3 over 3x minus 4 root 3. Better version, y equals root 3 factored out, 5/3 x minus 4. That's the better version, but we can keep this one. So, messier, obviously, but it makes sense, I think. So we start to find the tangent line. Again, I don't know where the tangent line fits in, right? But could. So to find the tangent line, you first figure out the slope. You figure out the slope by figuring out the derivative. You have the formula for it, and you have the derivation for it. So you find the slope. Once you find the slope, you use the conversion formulas for x and a y to find x and a y, because all you have given is thetas. And then you plug those in. So once you find your x is 3 and y is root 3, and you have your slope from before, just plug them in, figure out b, and there's your tangent line at the end. It's a procedure like any other Calc 1 procedure for the tangent line, except you have extra hoops to jump, because x and y are not given and all of that kind of stuff. So you have to find those. But it's a logical procedure, so yes, you can do it. All right, let's open the gates of hell. Integration. Lock the doors. So, I want to start this presentation by proving the formula for an area of the circle. We know what kind of horrors we encounter as we try to do this in xy coordinates. Is circle a function? No. Can we integrate circle as is? No, right? Can't. So what we have to do, we have to be clever, and we have to set up the integration for the circle. If you go x squared plus y squared equals to r squared, you have to start with y equals square root of r squared minus x squared, right? And that's the circle from negative r to positive r. And then you have to integrate that, so you integrate only the top portion. Oh, I forgot the plus and minus here. So you integrate only the top portion, which is using the plus of the formula, and you multiply by 2. So area of the circle would be 2 times the integral from negative r to positive r. And then you have the square root of r squared minus x squared dx. How do we integrate this? Trig sub, very good. You go with the trig sub, the r is the hypotenuse, the x is the leg, and you do the trig sub, and after 25 minutes, there we go, right? You do all the inverses later to bring it back to x domain. You use your negative r and r, right? It's nothing that 30 minutes can't do. What was the equation for the circle in polar coordinates? R equals to some constant, right? Whatever the radius was. That's your R. Whew. Isn't that nice? So how do we find the area here? Well, we learned the formula for areas for the polar. And the formula is that area is equal to 1/2 integral alpha to beta of r squared dr. Sorry, d theta. So what are alpha and beta? Input angle, right? The lower limit, and the beta is the upper limit, which is also the angle. Once you learn, the way to set this up, it becomes a second nature. You all know that you're going to get pi from the limits, right? So pi is incorporated in d theta. So what's the r squared pi? What's the area of the circle, right? So we understand the formula. There are subtleties with the half, which are in the part of the proof. So you can look it up. You can talk to me after the class or during the office hours. We can find that half. But other than that, I really hope that you see pi r squared right there. And that's just the area of the circle. Yes?
What is the capital R?
Capital R is whatever number you put in to be like 3 or whatever it is. It's a constant. Yes.
So it's just a constant.
Yep. All right. Are we ready to compute this? Now, this is the key point. Understand this right now. Look at it. I'm setting up the area integral. It's a 1/2 integral. I know it's r squared d theta. That's fine. But my limits, you see, you have now d theta. What is d theta? What is d theta? What is that thing? Yes, I call this representative pizza slice. You know when you set up the rectangular integrals like this, you had the representative rectangle dx, which was infinitely thin, and that was your dx. Now, in the circular world, you have this infinitely thin angle, d theta. I call it a representative pizza slice. D theta looks like this. It's at the center, stretching all the way to the function. So, if you recall, when we set up the f of x a to b, I said area is equal to integral of f of x dx, and I said that the representative rectangle starts sliding from a to b, from left to right. It swipes all of the values between a and b, so you put a and b here. Well, a representative pizza slice is going to start at the angle 0, and you ask yourself, how much of a circle do you want? Because it has to swipe that much. So what you have here is like the arms on the clock. You are at the 3, and then it's going to say, I just want a quarter of a circle. It goes 0 to pi over 2. Or I want a 180, right, which is pi, so it goes 0 to pi. I'll bend that way. So you simply swipe from 3 p.m., which is where the 0 is, counterclockwise to wherever you need to be. In our case, we have to go all the way around, so 0 to 2 pi. Let's go. Integration. 1/2. Integral is d theta. So this r was r, so I have 0 to 2 pi of capital R squared d theta, which is further equal to 1/2 integral of r squared is r squared theta, calculated from 0 to 2 pi. Right, this is the easiest case. Circle is just a constant. Then we're going to do the sine thingy, right? And it's going to be different. So now I have 1/2 r squared, 2 pi minus 0, and there's your pi r squared. So if capital R is 3, you get 9 pi. If capital R is 5, you get 25 pi. So no matter what r you get, you can compute the area of the circle. You get the idea what you can do with this, right? When you tutor that 7th grader, and you say, what was the area of the circle? Yeah, it was pi r squared. Why? Let's sit down. Look, this is why. Polar coordinates, boom. You start there. Not joking. Yes? Area. 2D. Area is 2D. And this would be the standard question, in my opinion, right, for honors to put on the exam, right? It's good. Nice little proof of the formula. And you get that the area of the circle is simply pi r squared, which we know. And now we know why. But the question is, what is the area of one petal of a flower? So, what is the area of one petal of a flower? R equals 4 sine 2 theta. Well, if you paid attention so far, you know that if you have an even number here, the number of petals is doubled. So you're going to have how many petals?
4.
4. And if that number is odd, you have that number of petals. So if that was 5, you would have 5 petals. Because it's 2 times 2 is 4 petals. If that was 8, you have 16 petals. So this number doubles the amount of petals. If it's even, if it's odd, that's the number of petals. So I want area of 1 petal, and I know that there are 4 petals on the flower. So the area that I'm looking for is going to be a quarter of the total area of the flower, because that makes sense. We have 4 petals, and I want area 1, so divided by 4. Now, we know the formula for area, so area that we are looking for is 1/4 times 1/2 integral. 0 to 2 pi calculates the area of the entire shape. 0 to 2 pi is supposed to trace the entire shape of the flower, or the circle, or whatever the hell you're talking about, cardioid and annulus and whatever else. So 0 to 2 pi is going to trace the entire object, so you can go and calculate 0 to 2 pi, and then you take 1/4 of it, because you want 1 out of 4 petals that you have. And then function squared, so 4 sine 2 theta squared d theta. So now it's a little bit spicier integral, but still possible. We have 1/8 outside, and then integral 0 to 2 pi, and then we have 16 sine squared 2 theta d theta, and this is usually where hell breaks loose. How do we integrate sine squared? Exactly. Oh, you're memorizing the answer. How do we integrate sine squared? Power reducing, thank you. So I should write 1 minus, you said what? Cosine of?
4 theta.
There he is, 4 theta. Let me just spell it out. 4 theta. Because it doubles whatever the amount of incoming, whatever is the incoming number, the formula doubles it. So if you had 16 petals, that would be 8, and in the formula it would have cosine 16. It has to double. The formula doubles stuff right there. All right, so that's these two, kills these two. And we can finally integrate. So we have a theta minus, integral of cosine is positive sine 4 theta over 4, computed from 0 to 2 pi. So we have a 2 pi over there, and then sine of 2 pi times 4 is going to be 0. 0 is going to be 0, theta is 0, so it's just 2 pi. If it's going to make you happy, here you go. All right, fine. Sine of 0 is 0, sine of 8 pi is 0. And then when you plug in 0 for theta is 0, so you have 3 zeros in a row. And the answer is 2 pi.
Can you also do from 0 to pi?
Ah, can I?
Yes. No.
But 0 to pi over 2 will work.
Oh, that's what I meant.
Ah,
Yeah,
okay.
that's what I meant.
Yes, well,
90
yes.
degrees.
All right, good. No, that's all good. I mean, we're all friends here for at least a week now.
Okay, yeah, that's what
So now, you have to be very careful with what Mark is proposing here. Mark is proposing, instead of using 0 to 2 pi and dividing by 4, which we can do when the stuff is symmetric, he's proposing to forget about the 1/4 there and use the values that will trace only one petal. Now, you have to be very good with graphing of these things to pull that off. Because it's not necessarily true that the area traced 0 to 2 pi over 2 is going to trace the first petal. You see, you have to graph this on your TI-83, 84 calculators because they are the last millennia technology and they graph slow. And because they graph slow and they plot pixel by pixel, you can actually see that the plot starts like this and then goes there and then goes there and then go, right? So when it started, you saw it started in the origin and traced this, and because it's a 1/4, sure. But see, the trick is that that part is traced 0 to pi over 2. Now what's happening with cosines? Cosines are laid out like this. Is it going to be traced from 0 to pi over 2?
No.
Hell no. You have to, for cosine, to get the same petal and get the same answer, you have to go from negative pi over 4 to positive pi over 4. Now see, that's the problem right there. So these things are not going to necessarily be traced for 1/4 of it, 0 to pi over 2. They will be traced with whatever is, and the best way to learn is to use the sluggish technology. So TI-83 is TI-84. If you have anything after that, it might not be tracing it slowly. But if you use TI-83, 84, they are sufficiently slow for you to see where the first petal goes. So when you do the cosine thing, I think it starts here, and then it goes like this, and then I think it goes down, and then I think it goes here, and then up there, and passes, and then boom. I believe that's the way the cosine graph goes. So you will learn this when you take the TI-80 whatever, right? If you have the right cell phones, right, you can download those calculators on the phone. And no, you have to use real phones, not the Apple garbage. So I gotta slide it in. I mean, I haven't, like, when was the last time?
You didn't take that much this
Steve
semester.
Wozniak didn't even buy the new iPhone.
My man. Yeah, I really slacked off on bashing on Apple. I feel like a failure, but
I mean, you don't have
that's
to, because Steve Wozniak didn't even buy it. He's like one of the founders. Right, he said he wasn't going to buy it. He said he won't buy it.
So yeah. Anyway, well, for the record, I hate Apple, all right? That's and they're garbage products. There we go. It's on the stream. So go ahead and unsubscribe. Yeah, I have zero respect for Steve Jobs and his terrible, terrible life and everything else. It's on the stream.
How do you do polar on the graph?
You have to go into POL, so mode, and then POL on the fourth line, the POL right there, so arrows. And you will, now your y equals screen gives you the r's, so you can plug in stuff. 4 sine 2 theta.
4 sine 2 theta?
Yes. Okay. So now that we know the basics, we are able to jump into some more interesting shapes. And again, since you guys are just learning this, having the graphing utility ready to see the trace, right, is really imperative. So let me pick up some problems from the book. Right? It's slow enough, right? So you can see which way it traces.
Yeah.
All right. By the time I get this book, so guys, in Calculus 3, you are going to add another dimension on top of this. So cylindrical coordinates are going to add z, and the spherical coordinates are going to add another angle, phi. And you are going to have a third-dimensional integrals dealing with these things. If you know polar coordinates well, which means you spent insane amount of hours now to really get this down, those sections in chapter 13 will not be an issue at all. If you don't know polar coordinates, it's hell on earth. I'm just going to show briefly one more time. Here are your representative pizza slices and the way they work. So your r equals f of theta are going to create some kind of curve. And then you have the representative pizza slices, which are parts of the perfect circle, but you see how they, right, go there. So these are little arches, right? It's round, so from a circle. But it's so small and so thin that it looks like a straight line. But you know that the pizza, right, is round, and when you take the slice out, right, and even if you cut it in half for a kid, right, it's still going to have that curvature. Now, when you look at a kid slice, it looks almost like a triangle because it's so thin up there, right, that you can't get the curvature from it. But if you take a look at like my size slice is just one large pie, you can clearly see the curvature. Yes. So that would be the representative pizza slice, and just propagate. There's the formula, right? Peeking out alpha to beta 1/2 function squared d theta. Those of you that are, into math, wondering and worrying that this is actually wrong because dimensionally doesn't make sense, just remember that d theta is not a dimension. D theta is a ratio. Theta is a ratio of the arc length to the radius. Angles are not dimension. So radian measure is simply the ratio if you have a pizza that has the perimeter in inches and radius in inches. Theta, which is the radian angle, is going to be the ratio of those two. So dimension of inches divides by the dimension of inches. And theta is radians, but it's like a dimensionless unit. So d theta does not give us dimension like dx gives us the thickness. So both of your area dimensions are in f squared. That's where the two dimensions are for the area in the r times r, and d theta does not contribute to that. This is the next step that I want to talk about, which is area between two of these, and you have the same thing for your rectangular world, where you have the top minus bottom, right? F minus g. Now you're going to have the one that is further away in terms of r from the origin where you measure to the one closer by. So we can calculate the area of the the washer, right? Metal. It goes under the screw. What? And the rest is from you. So,
I'm hungry. I survived.
growing one. Plus, if I chose one, then who's going to talk? You'll have to take over the class with that. Yeah, when I think better of it, I mean, even like with the SI, then you could just stay for the review. I don't have to come in with them. No, I'm just testing how much they like you. I know, I'm a terrible person 24/7. I was born that way. All right. So now we're going to move to the area between two curves. And we have the same formula, alpha to beta. Oops, you can't see what I'm writing. In a second, there we go. Alpha to beta. And then we have f of theta squared minus g of theta squared d theta. So this is the area between two curves. And again, we are going to understand this by, we can observe the annulus. So these are the circles inscribed like that. And then this one is the f of theta. And then the one on the inside is g of theta. So when you look at that, you will be computing the area of the washer over here as you compute this. So the one that is further away minus the one that is closer by. Yes?
Is there a reason you put the square next to the g instead of the outside one?
Well, if anything, I should bring this square closer to f. Because it's f and g that are squared. Those are the functions squared, not thetas. Boom. Yeah, it's a and b. Good. All right. Are you ready? So, I'm going to give you a drawing and ask for the area of the piece. Right there. What's the area of this part? Because of the symmetry, yes, but you can actually use the values that are there. If that's who can tell me what are the values in terms of pi's at these corners? That will be here. Let's try and ignore the symmetry. You have to, guys, you have to get in a habit of trying not to exploit symmetry, because in Calculus 3 it can really mess you up. Because you have to understand that this is going to be a pipe, maybe, where this part over here, where I colored, but all the way around, is a metal material, and then the thing inside is a hole through which, right, it's hollow, through which the water goes. Now, if you cut that pipe on an angle on top, right, then the volume that you get here would be different than the volume you get here, because the pipe is cut at an angle. Symmetry doesn't work, doesn't play nicely and easily moving to Calc 3. So I appreciate your ability to see that whatever you get for this area here would be the same as if you calculated 0 to pi. But what I need now from you is to kind of follow exactly what is shaded with exact angles for your alpha and beta, so that you don't run into trouble in Calc 3 when you say, oh, it's symmetric. Well, it's symmetric in a base, but now when you add the third dimension on top, it's not going to be symmetric, unless the pipe is cut perfect. Then, yeah. So what are the values? 3 pi over 4 and pi, thank you. So we have 1/2 integral 3 pi over 4, and then pi, and then, oh, I never told you the... So how about 4 and 2, huh? Is everything okay?
I'm not sure.
All right. So 4 squared minus 2 squared d theta. 4 squared, that's 16 minus 4, 12 divided by 6. Integral d theta, 3 pi over 4 and a pi, which is just 6 times pi minus 3 pi over 4, which is pi over 4, which is 3 pi over 2. I hope you can fill in the blanks. But that's the when you cut, right? This is halfway. That's pi over 4. Then 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6, 7, 8 pi over 4 is 2 pi. So you close the full circle. And now, as a grand finale, we are going to calculate the area. We're going to get something that is actually so we have the two shapes. One is r equals, so find the area between r equals 3 cosine theta and r equals 1 plus cosine theta. So one of these is a circle, and the other one is the annulus. No, the cardioid, sorry. So what do we have? We have a circle for the cosine one. When you shift the circle, that's what you get. And that goes through 3 over here. And then at 2, you have the cardioid. It goes like this. So this one is the 3 cosine theta, and this one is 1 plus cosine theta. I really can't help you with this. These graphs are freaking you out probably. Rightfully so, you never had these graphs before. It is just going to be investment of time to sit and figure them out. There is nothing that I can teach you about these shapes. You are either going to sit down, get your thetas, calculate your r's, you have r comma theta, plot, 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 and then connect the dots. If you're interested in that. You are going to graph everything you see. Maybe you're going to sit down. I mean, I know I asked you to do this last class, right, last week. So you are ready for this kind of stuff now. Now we're just using it. What shape do we want to calculate?
Another question.
Yes.
How come we did the circle not centered?
3 cosine theta is the circle that it's going between 0 and 3, so center is at 1.5 on x-axis.
Oh. Okay.
If I have r equals to 3, then it's centered at the origin, and the radius is 3 on each side. But this one is shifted, so it's, again, you guys will have to see and go ahead, check what 4 sine theta is. Right? Try to do some of these things. Now, 1 plus cosine theta creates the cardioid, oriented this way. Check what 1 plus sine theta is, and all these kind of things. So now say that you want area here. Like, what's that area? The first thing that I'm going to do is I'm going to draw the representative pizza slice from the origin. Right? There it is. Representative pizza slice d theta. Blue. D theta immediately tells me that it's a circle minus cardoid. Because d theta cuts through cardoid to get to the end destination that is circle. So circle is further away than cardoid. And the formula is set up as the one that is further away minus the one that is close by. Well, that's cool. So now I have 1/2 integral circle, that's 3 cosine theta, that's going to be squared, minus the one that it's close by, which is 1 plus cosine theta for the cardoid, right? And all of that in big parentheses d theta. Now, what are my limits? Well, I hope you see that everything begins here at the intersection, and then this little pizza slice will go through all of this and end up here. So these two intersections are your alpha on the bottom and beta on top. Well, the way to get these is exactly the same as in your first lecture of this semester when you set two equations equal to each other, and now go ahead, have fun, solve trig equations. I know. So we have 3 cosine theta is equal to 1 plus cosine theta. Cosine theta moves to the left, becomes 2 cosine theta equals to 1. Cosine theta equals to 1/2. Hit with the inverse cosine both sides, get inverse cosine of 1/2. And what's inverse cosine of 1/2? Pi over 3. So from there, theta equals pi over 3. Nice. Now is this alpha or beta? Pi over 3. That's beta, that's the top. So what's the bottom? Negative pi over 3. Nice. So, negative pi over 3, positive pi over 3. Just like in your... This is one of the reasons also why I love Calc2. You start the lecture and you finish up with the same thing at the end, except it's in polar coordinates. This is the first thing we did in the class, right? So, so there you have it. All you need to do is to crank the integral, and I'm sorry, that's Calc1. You're going to square some values, use the double power reducing formula. So there is some muscle to be put into this, but you know how to solve that integral. We only have 3 minutes left, so I would rather set up another problem than actually work this out. So I'm just going to say integrate integrate home. No, not home. Integrate at some point in life. At some point in life. What happened?
Forgot point.
Point?
At some point in life.
Yeah, at some point. Oh, word point. There. Oh, okay. Point. There we go. All right. Could have put point like that. Anyway. One more problem. I'm going to draw a flower. And a circle, let's say. So we have a circle. And then we're going to have a flower that pokes out, let's say. So this is a cosine one. Now, it shouldn't be that hard for you to see that the circle equation. I mean, you should be picking up that by now. What's the equation for the circle? R equals? From the picture. Yeah, what constant? No. Exactly. From the picture. I want the exactly from the picture. R is equal to what? 2. Thank you. And what's the formula for the flower? 3 cosine, how many petals? 4, so 2. Nice. See, you are getting there slowly, getting these graphs to like x squared. Oh, it's parabola, yay. All right. So, there you go. And now if I want, let's say, area over here, it's definitely flower minus the circle. Yeah. So, we are going to have 1/2, don't forget the 1/2, flower, which is 3 cosine 2 theta everything squared, minus the circle, which is 2 squared, all of that in parentheses, d theta. Please put those parentheses there, it triggers my allergic reaction.
Right to left. Triggers my allergic reaction.
Yeah.
It's right to left.
It's further away, because what if I do this one? Then it's left minus right. Your origin is origin, right? Origin. And then you measure from there. You go as far as you can. Right? It was easy for x and y, because you literally learn top minus bottom, right? Or right minus left. But now you are radially, right? For the sine, that it goes sideways like this, and you have a circle, right? That's cool. And now what do we do for limits? Set everything equal, right? And then now we are not going to get nice results here, right? Because this is all awful in terms of cosine 2 theta is equal to 2/3, right? We don't have the cosine for that. So we are going to have decimals in radians, right? As you apply inverse cosine to both sides, you get 2 theta is equal to inverse cosine of 2/3. Make sure that your calculator is in radians, and then compute the decimal value, and then divide it by theta, right? Divide it by 2 to get theta. So it's possible to do these things. I mean, nothing too crazy. And then whatever alpha and beta you get, right? Again, common sense. You will have a positive value. You will have a negative value. Alpha is the negative value on the bottom, and the beta is the positive value on the top, and you go from there. Which ends Calc2. No more. That's it.
Oh, this is the last class.
I'll see you in the spring.
What's a good window?
Yeah, see you in the spring for Calc2. Calc2.
You just can't get rid of it.
What's a good window?
I'll be right there. So I'm just say bye over here. That's it for the semester. Well, we have a review next class. Yeah, sure.